Okay, first of all, last section here, 12.5 on page 792. It's why this is important, such as the normal curve. There are many real-life applications such as IQ scores, heights and weights of males, heights and weights of females, wear-out mileage of automobile tires, whose histograms approximate a bell-shaped distribution. Understanding the properties of a bell-shaped distribution will help us determine the percentage of data that fall in certain intervals of the distribution of these real-life applications. All right, so the first thing we talk about is a rectangular distribution. In a rectangular distribution, all the observed values occur with about the same frequency, and this is what it would look like. So as a consequence here, the y-axis, which is your vertical axis, is the frequency, the amount you have. And so it's called a rectangular distribution because you can see that all your values, which are right here, have the same frequency. So this forms a rectangle. When you come out here, you have a J-shaped distribution. The frequency is either constantly increasing or constantly decreasing. Here's an example of these. This one is where, again, the vertical axis is always your frequency. Horizontal axis is your values. So you can see as you increase in your values going from left to right, the whole frequency increases. So this is an increasing distribution. Here, as you go from left to right, you can see that your values are decreasing. Your frequency of your values are decreasing as your values go up. Okay? A bimodal distribution is one in which two adjacent values occur more frequently than any other values in the data set. Come out here, another distribution is called skewed. And skewed is a lot like the J shape, but it actually has a kind of a normal distribution that leans to one way. In other words, like this one. This one is skewed to the right because our values, as they go up, they seem to go up to a peak and then go down. Here, this is skewed left because we start off low, we go up, and then we go back down. So see, there's always a peak in skewed left or skewed right, but what happens is you have a tail to the right for skewed right, you have a tail to the left for skewed left, okay? And normally we draw these like this. So what happens is we normally take a pencil and we usually draw a line that gives a good indication of how that skewness looks. So you can see how they get this, okay? Come over here, you need to understand that when you have skewed right data, then the median is found in the middle, just like we learned in the previous section. The mode is where the peak is, because that's the value that occurs the most. But the mean is to the right of the median. Okay? In skewed left, we have the opposite effect. Again, the mode is the peak, because that's the one that kind of occurs the most. The median is to the left of the mode, and then the mean is to the left of the median. So you can always make a prediction in terms of your mean being less than the mode and your mean being less than the median. Greater than, your mean being greater than the mode and your mean being greater than the median in skewed right, and your mean being less than the median and less than the mode skewed left. Now, talk about normal distributions, and then we're going to talk about it more. Normal distribution is what we call your regular bell-shaped curve. So see, if I take this and I draw this up like this, you can see that I get this bell shape. That's the reason the normal curve is called a bell-shaped curve. Okay? So normal distributions, the graph of a normal distribution is called a normal curve. The normal curve is bell-shaped and symmetric about the mean. So what they're saying here is that your mean is located at exactly where your mode is. So your mean, median, and mode on a perfectly normal distribution would be the same value. Okay? The mean, median, and mode of a normal distribution all have the same value and all occur at the center of the distribution. Okay? We have this here, and this is important because what happens here is, the normal curve is split up into what we call the empirical rule. The empirical rule says this, that your middle 68% of your data are found from what we call a z-score of 1, -1, and 1. So this right here, these would be the values where 68% of the values are found here. If we go -2 standard deviations out to the left and 2 to the right, we now have 95% of our values. And then if we go -3 standard deviations to the left and 3 to the right, we now have 99.7%. This is called the empirical rule. And basically what it says is approximately 68% of all the data lie within 1 standard deviation of the mean. Approximately 95% of the data lie within 2 standard deviations of the mean. And approximately 99.7% of the data lie between 3 standard deviations of the mean. Let's look at this one. It says heights for males that are the same age are normally distributed. Okay, so it's a bell-shaped curve. So we can use the empirical rule. In a random sample of 200 males of the same age, determine the approximate number of males in the sample who have a height within 1 standard deviation of the mean. Well, if we look back up here, if they're within 1 standard deviation of the mean, left and right, it's 68% of the data. So what we're going to do is take and multiply that 200 by 68%, which we got to turn to a decimal, 0.68. We find out approximately 136 of the 200 males measured lie between 1 standard deviation of the mean. Second part of that asks about lying within 2 standard deviations of the mean. So again, we do the same thing. We know that when they're within 2 standard deviations, that's 95% of the data. So we take 0.95 times 200 and we find out 190. Now you got to realize when we say 95% of the data, we're also including the 68% that we just calculated. So this 190 includes that 68% that we calculated here.